the decay occurs. So we've learned that in the real world, there's always a decay going on, so that if you want to maintain the oscillation, if you want to make the oscillation going and going and going, you must somehow feed energy into it to replace the energy that's lost through the decay. Okay, this is the restoring force, and this is the decay force. Okay, this is the force due to the presence of friction. In order to sustain the oscillation, you must feed energy into it, so we must introduce a new term to drive the oscillation. So we're looking at what's called a driven or forced oscillation. There are different forces that you can use to drive it. If we're looking for a simple harmonic expression for the final oscillation, then it's clear that the force that we want here wouldn't be something really funny like a square wave or whatever. We want it to be just a simple harmonic variation as well. Okay, let's say the amplitude of this force is F0. Okay, and it also varies as a sine or cosine function of time. So let's say it's F0 times a sine function of time. Okay, sine omega t. Now, this omega, by the way, can be anything I want. This is how the force varies over time, and it is not necessarily equal to the omega of the free oscillation. If you leave this thing alone, it's going to have a square root of k over m, right? That is not necessarily equal to this omega. This omega is determined by the driver, okay, by the driver. So I grab this spring and I shake it, okay? Depends on how fast I shake it. It has nothing to do with how, the spring is going to oscillate by itself. So that's the force. And that equals mass times acceleration. Okay, mass times acceleration. So this time I have one more term here. The solution is a little bit more complicated. As a matter of fact, it consists of two terms, okay? There is a transient term, and that is, that term is going to go away over time, okay? It only happens for a brief moment when you initiate the oscillation. And then it's followed by a steady term, which does not change over time, which goes on and on and on over time. Now, you can understand why there's a transient term. Imagine there's a spring and there's a mass, right? Nothing's going on at first. What you do is you grab that mass with its force, okay, and you start shaking it. Of course, the system is startled by that, right? It doesn't have an idea what's going on, right? It doesn't know how much force you want to pull it down with. It doesn't know how fast you want it to oscillate, right? So after a few cycles, okay, the system learns, oh, this is what you want me to do. You want to pull me down with this amplitude of force and with this angular frequency. So it learns to react, okay? There is a learning process which may take a few cycles. That is what's called a transient solution. We're not going to be bothered by that. Okay, we'll go straight into the next phase, and there is what's called a steady state solution. Okay, steady state solution. In a steady state solution, the amplitude of the oscillation no longer changes over time. Let's see physically why that is the case. Okay, because remember, the function of this term is to feed energy into the system. Now, initially, suppose it starts at rest. Okay, the oscillation starts at rest. So you take that force, you grab it and shake it, right? So initially, V is pretty small. You agree? V is pretty small. Okay, and of course, when you add this force, it's going to start oscillating, so V will increase. As V increases, this resistance force also increases. Now, this force feeds energy into the system. This force takes energy away from the system. Initially, because the motion is relatively slow, you feed more energy into it and less energy leaves the system. As a result, there is a net increase in the energy of the system, so the amplitude shoots up, okay? It increases over time. Now, gradually, as the amplitude increases over time, V on average gets greater, so the resistance force also increases, and then the energy taken away by this resistance force also increases. Okay? So, you have two competing sources. This one feeds energy into the system, this one takes energy away from the system. At some point, the speed reaches, the average speed reaches such a value that the energy you feed into the system per cycle equals to the energy that's taken away by resistance per cycle. So what does that tell me? It tells me that at that point, when that stage is reached, there is no longer any net change in energy of the system, right? Which means the amplitude of the system must be a constant. That is the so-called steady state solution. So in a steady state solution, I have just, a fixed amplitude oscillation. T and X. But please do not confuse this with a simple harmonic motion. This is not a simple harmonic motion. This is the forced harmonic oscillation. First of all, the frequency is not equal to square root of k over m necessarily. Rather, it's equal to whatever the driver wants. Okay, you grab it and shake it that fast, it's going to oscillate that fast. And if you grab it and shake it slowly, it has to do it slowly. Okay, the system has no choice as to what omega value it must oscillate with. That is dependent on the driving force. Okay, but that doesn't mean the system likes to be driven like that. The system can have its own reaction, right? It has its own reaction. Imagine, a child on a swing. Okay, you push a child on a swing like this, right? You know how you do that, right? When a child moves towards you like this, right? You don't push him back. Rather, you wait for him to come over and you give it a push, right? And the child goes forward with a greater amplitude. Then he comes back, you push it again, and it goes even higher. Comes back, push it even higher. Now, if the child swings like this, okay, by himself, like this, right? Like this. You don't want to grab his seat and shake it like this because, doing so is not going to be very effective in terms of increasing the amplitude of the swing. So that tells you that the system truly has no choice as to what frequency you want to oscillate, but it does have a choice of whether it likes the frequency or not. By liking the frequency, what I mean is that you are using a frequency, driving frequency, which is close to the natural frequency of the oscillation. The system oscillates like that naturally, and you are pushing it also like that. So that pretty much at every moment, you are pushing it in the right direction. When the system moves this way, you're pushing it this way. When the system goes back, you're pushing it back. So essentially, you're always doing positive work to the system. Okay, you're not resisting the motion. You don't go out of sync with the system, so that when the system goes this way, you try to push it that, then you're doing negative work, right? Okay, so when you are applying a driving force with essentially the same frequency as the square root of k over m, by the way, that's called the natural frequency. Natural frequency. Omega, let's call it omega naught, just to tell it apart, k over m. Okay, here's the natural frequency. If the driving frequency is close to the natural frequency, then what happens is that the system moves in sync with the driving force. So the driving force always pushes the system in the correct direction, giving it positive work. And that dramatically increases the amplitude of the oscillation, so that if we say this is a situation where the driving force is either too fast or too slow, it doesn't give you a very large amplitude, right? And then when the driving force is just right in frequency, it can give it a very large amplitude like this, you see? Like this. Okay, so what you have here is a simple harmonic variation as a function of time. So it's like sine omega t plus phi. But there is an amplitude. This amplitude does not change over time because, remember, this force and that force, they do the same amount of work over one cycle, positive and negative, so the amplitude does not change. But it does depend on the driving frequency. Okay, if this driving frequency is close to the natural frequency, A will be large, okay, because you're doing positive work, remember? And if omega is too fast or too slow compared with omega naught, the oscillation will not have a very large amplitude. So this is the physics. This is the representation of the so-called steady state solution. Now you can find what that A is. All you have to do is plug this into this expression, into this equation. Of course, you have to take two derivatives here. You have to take one derivative here, and so on. You can match it. We're not going to be bothered with that. That's just mathematics, but it's a little tedious, but it's certainly doable. What we want to know is the physics, and that is, what is the shape of A omega? Okay, we know that if we plot A as a function of omega, there is one frequency that stands out, and that is so-called natural frequency of the system. Okay, natural frequency of the system. If omega is close to omega naught, the oscillation will have a very large amplitude. When omega is too large or too small, the response of the system will be weak. In other words, you get a smaller amplitude. So you can expect something like this. Okay. So you see, around that natural frequency, if the driving frequency matches natural frequency, you have the greatest amplitude. And when the frequency is too large, too small, you can have small amplitude. This phenomenon is called resonance. And this is called the resonance peak. Okay, you can draw two possibilities. Let's say you have a curve like this. In other words, there is a resonance curve, but it's not pronounced at all. It's very shallow. Okay. Then you look at a situation, a different situation, like that. Look at that. That has the same resonance frequency as the first one, but the peak is very pronounced. Why is there a difference? Well, that depends on the mathematical details of A omega, which we're not going to get into. But physically, we can understand why there's a difference. If you look at these three forces, okay, now this force simply is responsible for providing the natural frequency, okay, right? This force is the driving force. Okay, its frequency will determine whether the system will have large oscillation, small oscillation. But what about that force? See, that is the resistance force. The resistance force is always opposite to the direction of motion, always slows things down. Does it care about whether the frequency is too high or too low? No, it doesn't. Okay, that term cares about whether the frequency is too high or too low compared with natural frequency. So the resistance force is insensitive to frequency. Okay, when B is small, then of course we're not going to worry about it too much, so that you have a very pronounced resonance peak like this. Because after all, this force, this term has an omega in it. When omega matches omega naught, you have very large oscillation and so forth. But when B is very large, then the system is dominated by the resistance force. You don't really care that much about, the next term, which is the driving force, so that the curve will not be very, sensitive to frequency. So you get a flat curve like that. Okay, it is clear that in many situations we want a very sharp response like that. Now, in this situation, we say the system is highly selective. Okay, it favors this frequency very pronouncedly and rejects almost all other frequencies. Can you think of an application of a situation like that? Well, this is a very discriminating curve. Okay, it favors only this frequency, it rejects everything else. Can you think of a situation where we want the system to be highly selective? Well, why not? How about a radio tuner, okay, or a television tuner? Our air is filled with all kinds of radio waves at all kinds of frequencies, right? How do you tune your radio so that you select only this particular frequency, okay, and reject all other frequencies? Because you don't want to listen to two radio stations at the same time, do you? Okay. And how do you do that? Simple. What you do is you tune the radio so that you adjust the natural frequency of the receiving circuitry. Of course, it's an electromagnetic oscillation, but the idea is the same. You are actually adjusting omega naught. Now, if omega naught matches the frequency of one particular radio station, then the signal from that radio station will enlist a very large response in your receiver, and neighboring stations with slightly different frequencies will be rejected. You see, so when you buy a radio or buy a TV set, you want a tuner that is highly selective so that you can pick up whatever frequency or whatever channel you want to listen to or watch. Okay, you don't want to buy something like that as a tuner, because then you're going to listen to a whole bunch of stations at the same time, because you see the response is not that different from one another. Okay, so that is the so-called resonance, and resonances have widespread applications in all areas of physics. It is sometimes a good thing, sometimes a bad thing. Like in the case of radio tuner, resonance is good. We want the resonance to be very pronounced. But resonance can also cause disasters. Okay? For example, if you have a bridge, okay, if you have a bridge, the bridge, being a mechanical structure, has its own resonance frequencies. It may not have a single frequency because the structure is complicated. You can have several natural frequencies. What does that mean? It means that if a force, if a natural force grabs that bridge and shakes it with that particular frequency, which is close to the natural frequency, that's going to cause the bridge to shake violently because there's a resonance, right? So when you design a bridge, you want to find a way to calculate, to predict these natural frequencies. And you want these natural frequencies to be far away from the natural oscillations that can occur around the bridge. For example, wind. Okay, wind can blow on and off. It's like rocking, like a force rocking the bridge, right? But if the frequency due to the blowing of the wind gets close to one of the natural frequencies of the bridge itself, that can cause a very large oscillation in the bridge that can even collapse the bridge. And I'm not just saying that as a theoretical possibility. I mean, this has actually happened. In the textbook, you see a famous example, okay, of the 1940 turbulent winds that set up a torsional vibration in the Tacoma Narrows Bridge in Washington. This is page 474, and that caused the bridge to collapse. So when they designed that bridge, one of the natural frequencies happened to be around the frequency at which the wind rocks the bridge. So that was a structurally bad design. So you want to make sure when you design a bridge, you don't design a bridge to have a frequency that is close to this range. So you can